Alright, in this video, we briefly review the calculus of complex valued functions with a real variable. So that means only those functions from real to complex numbers. These are necessary to deal with some differential equations and also Fourier series. So it's convenient if we summarize it here. So let's start. Rather than dealing with complex variables, dealing with real variables with complex values is actually quite simple because we can just treat the the imaginary unit as just another number which happens to have this property where that is when squared it's just -1. That's all. And otherwise, this I can be considered as just another constant. First, let's treat continuity. So we have a function g from real to complex. I mean, the domain can be any subset of real numbers, but let's say it's just real numbers. And we say this function is continuous if this if x goes to x0 and then g of x goes to g of x0, then we say g of x is continuous at x equal to x0. So it's just like the real functions. But what this actually means is that since this is a complex valued function, so convergence to this is, we haven't defined yet actually. So what this means is same as this. Limit x goes to x0 and the modulus of the difference between g of x and g of x0 is 0. Okay, and this also means, by the way, this modulus sign here means the modulus of complex numbers. Okay, so it's not just the absolute value of real numbers, but it's the absolute value of complex number. Okay, so what this means is both the real part, so real part of g, which is a real function, real valued function, uh, converges to the real part of g of x0, and at the same time, this limit x goes to x0 and the imaginary part of g of x converges to the imaginary part of g of x0. So this real part and the imaginary part, they are real valued functions. So we can deal with them just like any other real valued functions, which is already clearly defined. So that's what we mean by a continuous function for a real complex valued function. Okay, next consider differentiation. So we say again g is a function from real to complex, and it is differentiable at some point if and only if both the real part and the imaginary part are differentiable. Okay, in this case, if we differentiate it with respect to x and evaluate it at, let's say, x0, then that is given by the derivative of the real part of g plus the imaginary unit times the imaginary part, the derivative of the imaginary part, and dx, and evaluated at x0 each. Okay, so this is what we mean by differentiating a complex valued function. Okay, let's see an example, simple example. Let's say lambda is any real number, and we have this Euler's formula. Exponential of I lambda x is cosine lambda x plus I sine lambda x. So this is the real part, and this is the imaginary part of this function. Okay, so if we differentiate it, the derivative is given by, so the derivative of this one, so that is negative lambda sine lambda x plus, and the derivative of this, so that is I lambda cosine lambda x. So this is the derivative of the real part, and this is the derivative of the imaginary part. And the sum gives the derivative of this complex valued function. Very simple. By the way, the mean value theorem does not apply to complex valued function. That's because the complex number is not linearly ordered. So for any real numbers, we can always say, for any two real numbers, we can always say which one is bigger or which one is smaller, or if they are equal or not. But in the case of complex numbers, there is no order. So we cannot say which complex number is greater than what complex number. So because of that, the mean value theorem doesn't apply to complex valued functions. For example, again, consider something like this. Let's see, g of x is equal to exponential of ix on this interval from 0 to 2 pi. Okay, and we have g of 0 equal to 1 and g of 2 pi equal to 1. So they are both 1. So if the mean value theorem applies, then there is some x between 0 and 2 pi at which the derivative of this function becomes 0. However, the derivative of this function is this, I exponential of ix. And the modulus of this function, the derivative, is always 1 because of this. So there is no, let's say, xi in this interval such that g prime of xi is equal to 0. So there is no such value. So that means the mean value theorem doesn't hold for this function. All right, next let's consider integration of complex valued functions. Again, let's say g is a function from real to complex. Then the definite integral on the interval between a and b of this function, remember x is always real, is defined by this, the sum of the integral of the real part of g of x, so this is a real function, plus I times the definite integral of the imaginary part of the function. Okay, again, this is a real function. So if these integrals are defined, I mean, if they converge, then we can define the integral of this complex valued function. And that's, I think, straightforward. And many of the properties of definite integrals also apply to complex valued functions, as long as it makes sense. For example, first, we have this property derived from the triangle inequality. The absolute value of the integral, so this is the modulus of complex number, okay? So that is the square root of the sum of squares of the real part and the square and the imaginary part. This is less than or equal to the integral of the modulus of the function. Okay, so this holds also for complex valued function. And second, if g of x is continuous on the interval between a and b, then let's define this uppercase g of x by this integral g of t dt. Then let this, and then the derivative of this uppercase g of x is given by lowercase g of x. So this is the fundamental theorem of calculus. And if, conversely, if g1 of x is a primitive function of g of x, so that means g1 satisfies this equation. So if its derivative is equal to lowercase g of x, then we have the integral of g of x from a to b is equal to g1 of b minus g1 of a. So another expression of the fundamental theorem of calculus. So here's an example. Okay, so let gamma be any complex number. And let's integrate this exponential of gamma x. Then we have, so this can be integrated just like any real valued functions, as if this gamma is a real number. So 1 over gamma exponential of gamma x from a to b, and that is exponential of gamma b minus exponential of gamma a over gamma. So this is the result of the definite integral. So as you can see, the complex valued functions with a real variable are very easy to handle. So they behave much like any other real valued functions. If the variable itself is also a complex number, then everything is different, and it's beyond the scope of this lecture series. And you should learn that in complex analysis. But anyway, that's so far that's all we need, and that's all for this video. And see you later.